So continuing in section 7.1, dealing with radicals and fractional exponents, we're now basically into the second half, right, which deals with the fractional exponents, okay? And what ends up happening is you learn that we had been dealing with expressions that were in radical form, right? You know, square roots, cube roots, nth roots in general. But what it turns out is that when you're dealing with radicals, right, which use that symbol there, right, which is the radical sign. I mean, of course, it has different, you know, indices, right? The plural of index. You put different numbers there where the n goes, like that can be a 3 for cube root, a 4 for fourth root, so on and so forth. So you use that radical sign with radicals. They actually correspond to fractional exponents, okay? And how do we change from radical form to exponential form? Well, we basically just think about this saying here, which a student told me a long time ago that I guess one of their high school teachers told them. You use this phrase, the power is the flower and the roots are under the ground. Okay? And what does that really mean? It means that the root of the radical expression becomes the denominator, right? The roots are under the ground. So what you do is if you think of a fraction, right, the fraction bar is kind of like the ground. So the root of the radical expression becomes the denominator because that's under the ground, and the power of the radical expression becomes the numerator of the exponential expression, right? The numerator of the fraction, because the power is the flower. So the power is the flower, which would be above the ground, and the root is under the ground. Okay, so the power becomes the numerator, and the root becomes the denominator. So if you just remember that phrase, you should be good. Okay, so the idea is if you have something like the square root of x to the third power, okay, well, what does this mean? The power is 3, right? So I know that this is a radical, right? So I can write it as a fractional exponent. So this is going to be equal to x to some power. That's a fraction. So I write my little fraction bar here. And this is the power, 3. So it becomes the flower, which is the numerator. And the root, even though you don't see it here, when there's no root written, it's an assumption that it's a square root, which is really a 2. So in this case, the root is 2, and the root goes under the ground. So it's really x to the 3/2 power. Okay? So this is a pretty straightforward process, right? So if you had something like the cube root of -8 squared, this would actually be the reverse, right? This would be -8, right? That's my base. And then in this case, again, it's a fractional exponent. The power is 2, so that becomes the flower, which is above, you know, the numerator. And the 3 is the root, which is under the ground, so that's the denominator. So that's actually -8 to the 2/3 power. Alright? And that top one there, right, the square root of x cubed, that one, you know, if you just write it as x to the 3/2, there's nothing else you can do to it. You can't evaluate it. However, the cube root of -8 squared, you can evaluate, right? Because the cube root of -8 squared, you would realize, hey, all right, well, I guess I can square the -8, right, and get 64, and then take the cube root of 64, which is going to be 2. Right? I'm sorry, 4. Right? So you would square -8 and you get 64, and then the cube root of 64 is going to be positive 4. Okay? So this is actually just going to come out to be 4. Okay? So what's more typical actually in these kind of problems is they might give you like an expression in exponential form. So they might give you something like, all right, well, let's say we have 25 to the 3/2 power, right? What would 25 to the 3/2 power be? I'm doing the reverse now, right? I would say, all right, well, 25 to the 3 halves, there's the flour, the 3, so that actually becomes the power. So it's 25 to the 3rd, and that's under the ground, the 2, so that's going to be the root. So it's actually the square root, right? Again, you don't write the 2, but you assume that's a 2 there. So this is the square root of 25 cubed, and now let's evaluate this. Now, in the other one that I did, the cube root of negative 8 squared, it didn't really matter whether I squared or took the cube root first, because I was dealing with, fairly small numbers. But here, if I cube 25, I have some huge number, which I'm not going to be able to know what the square root is. So in this case, it's actually easier to do the root first. So if I do the root first, right, the square root of 25, so what I'm really doing is I'm really looking at it like this. I'm really looking at this like it's the square root of 25 and then cubing it, right? So if I take the square root of 25, I end up with 5, and then I cube 5, and I get 125. So the way these problems usually are laid out is they'll tell you, all right, first convert it to radical form. And there it is in radical form, right? So that's like one answer, right, in radical form. And then they'll say, and then evaluate. And then when you evaluate it, you get a single number, which in this case is just 125. All right? And I had that little note about the calculator here. When entering these fractional exponents into the calculator, the exponent must be inside parentheses. Of course, unless you have an updated calculator that actually, when you do the exponent, it actually puts it in that superscript position, so then you don't have to worry about the parentheses. But the calculator that I have is more basic, so it's the older version, just the TI-83 here. So if I wanted to do 25 to the 3 halves, I'd actually have to do this like this, 25 caret, and then parenthesis, 3 divided by 2, and that's going to give me the 125, which I ended up with. Now, can the calculator also enter in the square root of 25 cubed? Sure. You can just actually hit the square root button, right, which is second x squared, and then I would do 25 cubed, right? So the square root of 25 cubed is also going to give me 125. All right. So either way, you'll get the correct value there. And one other thing to note, because we didn't throw in any of these ones here. Say you had something like 8 to the negative 4/3 power, right? You're still going to use the same rule. The power is the flour, the roots are underground. But the problem here is we have a negative exponent. So when you have a negative exponent, what does that mean? It means you do the reciprocal. So the reciprocal of 8 is actually 1/8. So this would really be 1/8 now to the positive 4/3. Okay? And of course, it doesn't matter what the 1 is raised to. 1 into any power is always going to be 1. So this is really just 1 over now 8 to the 4/3. And again, we're using that phrase. The power is the flour, the roots are underground. So in this case, the flour is 4, so this is 8 to the 4th, right? The flour is the power. And the root is under the ground, so the root is the 3, so this is actually going to be the cube root of 8 to the 4th. Okay? And now again, so that would be it, the expression written in radical form, and now you would evaluate it. So what is this equal to? Again, I wouldn't want to do 8 to the 4th because it's a huge number. I'd want to do the cube root of 8, which is 2. So I'd have 1 over 2 to the 4th, and of course 2 to the 4th is just 16. So this is just 1/16, right? And that would be it evaluated. Okay? So now you've evaluated it. And of course, I can do this on the calculator also in 2 different ways. I can do 8 caret, let's see if this is visible. Yeah, 8 caret parenthesis negative 4/3 which is going to be 0.0625, and then if I turn that into a fraction, right, hit math, go to a fraction, and it's 1/16. So that's right. Or I could actually write it in the radical form, and if I wrote it in radical form, I'd have to write it like this, in that yellow highlighted expression, 1 divided by, and the cube root, how do you do the cube root? If you push the math button, there's actually a command for cube root. There it is. Cube root of 8 to the 4th. Right? So I have the cube root of 8 to the 4th power, 1 over that, and that's again going to be 0.0625, which is the same thing we got for 8 to the negative 4/3, which, as we saw, was 1/16. So you can write it in either form there, and you get the same result. Now, as it turns out, I mean, which you would pretty much expect, because math always works out nicely like this, right? Every exponent rule, right, that we dealt with prior to radicals that just had integer exponents is still going to apply when dealing with fractional exponents and thus radicals, right? Which we'll see in a second. So in other words, if I give you if you were given something like this, x to the 2/3 times x to the 3/4, you use your same exponent rule, right? When we have the same bases and they were being multiplied, you just add the powers. So you would just be adding 2/3 and 3/4. So this is really just x to the 2/3 plus 3/4. So, I mean, the only tricky part here is you have to get a common denominator, right? Which is, in this case, 12. So this is really 8/12 plus 9/12. So this is actually x to the 17/12, which is a wacky power, but, I mean, that's the way it works, right? So when you have the same bases and they're being multiplied, you add the exponents. And then, of course, when you divide, like, so if I was dividing x to the 1/4 by x to the 4/5, what do you do when you divide? You just subtract the powers. And I'm not sure we had actually talked about this, but you know when you have a division problem like this, the result, right, the final answer is going to end up wherever the higher exponent was. So in this case, what's bigger, 1/4 or 4/5? 4/5 is bigger. So what I'm really going to do here is I'm actually going to write this as 1 over, and then I'm going to do 4/5 minus 1/4, right? So I would actually be doing 4/5 minus 1/4, and realize that my answer is going to be in the denominator, right? And in this case, LCD is 20, so then this is actually going to be 16/20 minus 5/20. So 16 minus 5 is actually 11. So that's actually 11/20. So this is really 1 over x to the 11/20, right? And again, I mean, these are wacky problems, wacky results, but I'm just trying to show you that it doesn't matter how wacky they are. You're still using the same exponent rules that you were using, right? And then, of course, the other one is if you have a power to a power, right? That was the other big one, right? I mean, there's more than just these three, but the other main one was you have a power, like so. All right, so let's say you have x to the 1/2, and then that's raised to the 1/3. This isn't as wacky as the other ones were, right? So when you have a power to a power, you multiply the powers. So this is really x to the 1/6. Okay? So it's pretty straightforward, right? Your exponent rules carry over to fractional exponents.